morning.
Morning, Rashid.
How are you?
I'm fine. What about you?
Very
It's going on, I think.
Yes.
Okay, that's good.
Are you ready?
Yeah, yes, I am ready, but Alberta is here. Alberta,
Okay.
I am ready, I think.
مظبوط. شو 24 ترجي الجنية ترجي الجنية ترجي
Ok. Professeur, ok. C'est bon. C'est le moitié, c'est bon. C'est bon.
يقول لي رحمه الله بروفيسور كون كنقول وي كان
Okay. Okay, Professor. Okay. Again, morning, everyone. This is my pleasure, of course, to being here. And firstly, I would like to thank the organizing committee for bringing us together in such a nice conference. And in this first session, I think, of this conference, I want to introduce the Dr. Alberta Terzi. She will present us, will share us a work on type 1 collagen, which is the main table-forming protein of the extracellular matrix, which provides mechanical support for tissues and organs. And Alberta Terzi has a postdoctoral researcher at Institute of Crystallography, National Research Council in Bari, Italy. And her main research fields are on X-ray structural characterization of the extracellular natural polymers in physiologic and pathologic tissues and their applications for the development of engineered tissues for regenerative medicine. In past, she not so far past. She performed some experimental works at Swiss Life Source at Paul Scherrer Institute during her PhD thesis times. Also, as I can see, she worked for 6 months at Remodel Regenerative Modular Developmental Engineering Laboratory of the National University of Ireland, Galway. And this is very important. She received the Best PhD Thesis Award 2019 from Italian Society of Synchrotron Live. Congratulations, Dr. Terzi, for this special award, and good luck to your future academic career. And if you are ready, you can share with us your presentation. The title is, we can see here, X-ray hierarchical investigation of type 1 collagen in tissue engineering and pathology. Okay, Dr. Terzi.
Thank you.
You're welcome.
First of all, thanks for the introduction, and I want to thank the organizers of the conference because they give me the opportunity to be here and to share our works. In particular, today I'm going to talk about X-ray hierarchical investigation of type 1 collagen used as biomaterial for scaffolds fabrication in tissue engineering and evaluation of structure of type 1 collagen in different pathologic tissues. Briefly, I want to introduce you the extracellular matrix that is the background of our body, in particular the background of each tissue of our body. It confers mechanical support to tissue, the thickness and elasticity. In particular, it is different in relation to the tissue in which it is. And it is also a scaffold for cell attachment and migration, not only during fetal life, but also during the adult life. After injuries or tissue damage, it acts as a scaffold for the regeneration of the tissue itself. As I said, the extracellular matrix is different in relation to the tissue in which it is. For example, here I show you two pictures of two different tissues. In the skin, we can see the extracellular matrix that is organized like a network, because in skin we have a multidirectional load, mechanical load, so the extracellular matrix allows to support this load. While in tendon, we have an extracellular matrix oriented along a specific direction. That is the direction of the mechanical stress and stretch on the tissue itself. This matrix is made with different proteins, different glycoproteins, small molecules, and water molecules. In particular, the most abundant protein that we can find in it is type 1 collagen. It is a specific and characteristic protein with a hierarchical organization. Starting from the atomic scale structure, we can find the triple helix of collagen, more than one, in particular 5, can arranged into fibrils, and fibrils arranged into fibers, and so on, till the bundles and at the micro scale. There are several works about the structure of type 1 collagen at the atomic scale and the identification of the nanoscale structure of this protein. But what about the multiscale integrity of type 1 collagen when it is used for scaffolds fabrication? So after the extraction of this protein from a tissue and manipulation of it for the fabrication of scaffold. And what about the multiscale integrity of this protein within pathologic tissues? These are our focuses, the focuses of our works. In particular, we performed analysis at X-ray microimaging laboratory in the Institute of Crystallography at CNR in Bari. That is a lab equipped with the X-ray synchrotron class rotating anode microsource for the structural study of biological tissues and bioengineered tissues. The X-ray beam is focused through multi-layer focus optics and collimated by 3 pinholes in order to obtain high spatial resolution configuration and high flux configuration. We can perform different kinds of measurements. In particular, we performed on collagen wide-angle X-ray scattering technique in order to evaluate the atomic scale structure of collagen, and small-angle X-ray scattering technique for the evaluation at the nanoscale, so VAX and SAX. Both these techniques can be done even simultaneously. And moreover, we have also the opportunity to perform scanning microscopies, for example, on pathologic tissues, to probe the tissue itself. This slide I want to show you what I mean when I talk about this kind of measurements on collagen. In particular, this is a typical 2D diffraction pattern of VAX, so molecular structure of collagen, we can see from this pattern, of one of our samples. This is a type 1 collagen extracted from equine tendon. All the signals that are located along the red arrow are called meridional diffraction signals and are related to the structure of collagen along the molecule, so along the triple helix. In particular, they are related to the distance between two close amino acids along the central axis of the triple helix, and are related to the periodicity of the single triple helix. All the signals that are located along the black arrow, so orthogonally directed with respect to the red arrow, are called equatorial diffraction signals and are related to the lateral packing of collagen molecules within the supramolecular structure of fibrils. This value is variable, and the variation of this value is related to the hydration state of the tissue or of the collagen itself, because it is well known that collagen is well stabilized by a cylinder of hydration that allows the formation of hydrogen bonds for the stabilization of triple helices. So the information along these two directions, the striking information that we can obtain and that we can extract, allow us to define the collagen as a liquid crystal. The 2D diffraction patterns can be folded in 1D diffraction profiles, identifying the two main peaks of collagen that are the meridional diffraction peak in the red box and the equatorial diffraction peak in the black box. In particular, we can also evaluate the distribution and the order of collagen molecules within the tissue. For example, we can analyze the full width half maximum of the equatorial diffraction peak that is related to the lateral packing of collagen molecules, obtaining information about the extension of crystalline domain of collagen within the tissue. Here, I show you two examples of 2D diffraction patterns and 1D diffraction profiles from equine tendon collagen and fish skin collagen. You can see that there are some differences. In particular, in equine tendon collagen, we can see all the meridional diffraction signals, meridional and equatorial signals that are strictly preferred oriented along the directions. This is not like this for the collagen fish skin, because it is randomly oriented within the tissue. After the evaluation at the atomic scale, we can also evaluate the collagen at the nanoscale. As I already said, the triple helices can assemble within a supramolecular structure called fibril. The fibril possesses an axial periodicity that is related to the distribution of electron density along the axis of the fibril, and we can see this distribution through the 2D diffraction pattern sacs. As you can see from equine tendon, we can see a periodicity that is clearly striking observed along the red arrow, and that we can observe in the profile, 1D profile from these peaks. The variation of the profile's intensity is due to the variation of the electron density distribution along the fibril. This information is not clear in collagen from fish skin, for example, also because also in this case at the nanoscale we don't have the same structure that we can observe in the equine tendon. So why we focus the attention on type 1 collagen? Because it is a gold standard for the fabrication of scaffolds in tissue engineering because of its biocompatibility, biodegradability, hemostatic properties, it confers mechanical support to tissues during the regeneration. It is a gold standard for the top-down approach or traditional approach in scaffolds fabrication. That means to extract type 1 collagen from a tissue and then to manipulate it in order to obtain the final medical device. And it can be used as a gelatin form, so in the denaturated form, or in the native form. First of all, we wanted to analyze the raw materials, so the raw type 1 collagen extracted from different sources, in particular fish skin, bovine dermis, and equine tendons, in order to evaluate the extension of crystalline domain of collagen once extracted from the tissue. In particular, we analyzed the full width at half maximum of the equatorial diffraction peak, the one related to the lateral packing of collagen molecules, identifying that we can obtain a higher extent of crystalline domain in type 1 collagen extracted from equine tendon with respect to the one extracted from fish skin. This highlights the importance to the choice of the right extraction tissue when we want to fabricate a scaffold. In this work, we identified a more useful fabrication treatment for the production of scaffold for the action and regrowth, and highlighting the relation between the structural features and the cell differentiation. In particular, in this work, we identify the homo treatment, apparently the most aggressive process that we can perform on the material, as the only one that assures to obtain a material with a high content of triple helices within an extended crystalline domain, stimulating the higher expression of the differentiation factor CROX20 within Ratschanoma cells. This is possible because the well-organized structure of the material, so the higher extension of crystalline domain, helps the cells to recognize the material through the exposition also of binding sites for cells themselves. So once identified the best treatment that we can use for our purpose, in this case the fabrication of scaffolds for axonal regrowth, we investigated the effect of this treatment on different collagen from different sources. Also in this case we wanted to identify the order of triple helices within the material, and we analyzed the full width at half maximum of the equatorial diffraction peak. Identifying also in this case a higher extent of crystalline domain in the biomaterial made with collagen from equine tendon with respect to the one obtained from collagen from fish skin. In particular, the biomaterial made with type 1 collagen from fish skin possess a lower extension of crystalline domain that can be ascribed to the fact that the fish is a cold-blooded animal, and we know that in cold-blooded animals we have a less percentage of lysine and hydroxylysine, that are the sites for the cross-linking, and this means that this type of 1 collagen is less stable than the one that we can extract from warm-blooded animals like the bovine or equine. So we performed experiments for the characterization of the atomic scale structure of collagen. But what about the nanoscale? Is it important? First of all, we identified the presence, the partial retention of the nanoscale structure of collagen only in the material extracted from equine tendon. Moreover, as you can see from the 1D diffraction profiles that are in the bottom part of the slide, during the fabrication process to obtain the scaffold, we have a partial decrease of intensity of the periodicity, so of the structure at the nanoscale. Moreover, it was also identified an effect made by the nanostructure, the shield effect. This means that the nanostructure of collagen can act as a shield toward the atomic structure of collagen itself, and this means that every manufacturing process that we can perform on this kind of material doesn't affect the atomic scale structure of collagen, but only the nanoscale structure of collagen. And this is possible only in materials with a hierarchical organization, a retention of a hierarchical organization. Concluding, what we want to show with our results is that the evaluation of the order of the collagen molecules and the collagen fibrils within the material, it's an important step in the characterization of the scaffolds and in the characterization of the material used for the scaffolds fabrication, because allows us to identify the right tissue from which extract the collagen, the right collagen to use for the scaffolds fabrication, and the right processing for the medical device production in relation to the tissue that we want to regenerate. In this slide, I want to show you the combination of VAX and SAX techniques and the application of the scanning microscopies to pathologic tissues. For example, here we have aneurysms from abdominal aortic and popliteal artery. Through the combination of these two techniques, it was possible to identify the alteration of the organic part of tissues, such as collagen, elastin, filaments, and the alteration at both the nanoscale and the atomic scale of each part of the tissue itself. In particular, it was also possible to identify the phases of the microcalcification that are embedded within the organic part of the tissue. There are several other applications that we can do on with the X-rays. For example, the characterization of fiber-like polymers that can be artificials or natural. For example, pegylated tetraphenylalanine or cellulose or fibrin. And there is a world of analysis that we can perform. I want to thank the Institute of Crystallography and Director Professor Saviano and my group leader Cinzia Giannini and all the people I work with and I worked in these years, all the collaborations. I want to thank you for the attention, and if you have any questions, I'm here.
Le micro, s'il vous plaît.
I cannot hear.
Merci de débloquer le micro, s'il vous plaît.
We cannot hear you. We cannot hear you. Please, we cannot hear you.
Dr. Konkagul,
Yeah, yes.
activate your...
No, I don't activate it again. I told myself. Okay. Okay, sorry. Thank you, Alberta, your presentation. Is there any question? If don't, I want to ask some small question to Alberta, just my personal curiosity, Alberta. For maybe several years, we realized that the collagen is very important to our healthy daily life. And the people talked about, actually my doctor advised to me, you need to use type 1 and type 3 collagen. And there are, I think, just only 3 type collagen. Or not, I don't know.
No, if you are talking about fibril forming collagen, the most abundant is type 1, but we also have type 3 and another couple of collagens. But then there are also collagens that are not fibril forming,
okay.
can be widely spread within the tissues.
Okay, thank you. I didn't know that. Okay. You investigate type 1 collagen and you
Yes.
talk about it is in liquid crystal form. Okay?
Yes.
Okay. This collagen is soluble in water or not?
It depends, because when we use collagen for scaffolds fabrication, it is in acid-soluble form. So the companies
Okay.
generally produce acid-soluble collagen. This means that it is not so soluble if you don't treat it before.
Okay. Okay. Just because out there are many types of collagen collagen to use in daily, and some of them is as filling and another is liquid form. Which one is more useful to us? I mean, solid or collagen in its film form or its form.
Sorry, I didn't understand. I can say to you that I use the collagen flakes.
Okay.
Okay, so I use some dissolution. I dissolved the collagen flakes, and then after the production of slurries, I performed all the manufacturing processes in order to obtain the material. So I don't understand what you mean when you say which kind of collagen.
Which type of, I mean the physical state.
Okay.
Solid or liquid form. Just
I
use liquid form collagen shot. Just shot.
Ah, okay. No. That one I think
sometimes it's used. It's soluble. They put into in water.
okay. No.
Okay. But
In the
I
solid
just
form.
only use liquid form.
Okay. No, in the solid form. I used it in the solid. It
Soluble
was
form.
flakes.
Okay.
Flakes of collagen.
Okay. Thank you, Alberta. Thank you. Very interesting presentation for me, especially. Okay, is there any question?
Of course, if you mind. Okay.
Okay, probably there is no another question.
No, I have question. Thank you.
Okay, sorry.
Professor Alberta Tirzi.
Sorry, okay.
Very nice and interesting lecture. You talk about complement of elements in nutrition of collagen. My question is what the best collagen is originally from animals, fish, or vegetable? The first question. The second, when you speak about solubility, you speak about what kind of solvent, water, organic solvents, or what else?
Okay. For the first question, I can answer that. Okay, let's start from the last one. So I use the different solvent for the dissolution of collagen. Let's start for the last question. So I use acetic acid. I used water. Principally these two kinds of solvents. But then I also performed some physical treatments in order to, like homogenization, in order to obtain a good solution of collagen. For the first one, I can say that there is not the best collagen. I can say like this because, as I said, the structure can be important in relation to the tissue that you want to regenerate. In this case, in my case, I worked on the scaffolds for the tissue regeneration. So I think that you have to choose the one that you think is the best for the tissue that you want to regenerate. For example, if I want to regenerate an hard tissue, maybe I will use I can use a well-structured collagen. Can be better than use a collagen that is more amorphous or a gelatin that is a hydrolyzed collagen. Or if I want to regenerate, for example, the axon, maybe it's better to use a collagen with a nanostructure because it can be a guide for the axonal regrowth. So to use the structural features of collagen for the tissue that I want to regenerate. So I don't think there is the best collagen. that is the best for my purpose. Let's say like this.
Yes. Also, when you speak about micro calcification.
Yes.
Because
pathologic tissues.
Yes, because collagen is widely used in Morocco in meals of cow legs. They are cooked and they present emulsifient sauces and are very good and are very recommended for meals for those who suffer from bone articulation. Of course,
is a complement.
I think that microcalcification is also induced in to care and to regenerate bones in squelettic in human squelettic.
But is this a question?
Yes, remark. It's an observation that all people believe that collagen can be useful to patients who suffer from articulation.
Yes, there are some alimentary complements, or there are also the fillers. Fillers made with collagen, with the denaturated collagen, or with different kinds of collagen, not only type 1.
Yes.
Not
But
only type 1.
We know that collagen is generally extracted from wild boar or pork. Yes.
Yes, generally, yes.
Yeah, yes. Professor.
Manufacturing probably. I understand. I see you, Dr. Hammoudi, because in Turkey we similarly, I think, the collagen from type 1 and type 2 probably. Animal sourced meals, cooked meals. We got the collagen, these meals, and bovine collagen, as we hear that, as we can hear that. Bovine collagen is the best for the health.
Yes.
I don't know.
Yes.
I don't know how much it is true, but also I use the additional manufacturing collagen, of course, just because it does not enough my daily routines to get the collagen, 3 type collagen from the meal or my diet.
Okay.
Okay, that's not question. This is the liquid collagen.
Yes.
I use that.
Professor Kokakul, can I have a question?
Yeah.
Oh, yeah, yes, please. Yes, please.
Thank you so much.
Professor Rashid, please.
Thank you so much, Professor Alberta, for this nice lecture. In the first conference, Professor Abidi from United States speak about polymer. What about preparing mattress, mixing collagen with, for example, polymer to have very good and efficient properties for multiple applications? If we can mix, for example, polylactone or such polymer to increase the properties. Thanks.
Yes, there are several works about this for the fabrication of scaffolds in blend with collagen in blend with other biomaterials. That this could be useful. The only thing that I want to recommend when someone fabricate a scaffold is to to take attention to the treatment that is used for the fabrication of the scaffold, because sometimes, for example, if we decide to use collagen, well-structured collagen, such as the one from equine tendon, and we want to use it in blend for example, the formation of a scaffold with electrospinning, we will lose the structure of collagen. So when we use, when we perform a treatment for the fabrication of scaffold with collagen in blend with something else, we can have an alteration of the structure of collagen, and it is important to probe the biotissue in order to evaluate if this kind of alteration can be useful for the regeneration or not. Can be, for example, a starting point for the exposition of binding sites for cell attachment, or not. So it's a point, so a particular point. This is the importance of X-rays, because X-rays helps to identify this alteration and to correlate this alteration to the behavior of cells on the biomaterial.
Thanks a lot.
Please, a question from Dr. Azzawi from the south of Morocco. Speak about if you can add molecules or ion on the collagen matrix, and also is it possible to test clinical use in therapeutic and medical vision?
Yeah. Yes, sure. It is possible. It is possible through conjugation, because collagen has binding sites, has some parts that can be modified in order to form bonds with small molecules. It is possible to functionalize it. And to study the release of the small molecule that can be, for example, a differentiation factor or something like this. Studying the release, we can then see if this medical device can be useful or not. Can be useful also for example, we can conjugate small molecules with antibiotic activity.
Yeah.
So studying the release, we can see if this is useful or not for our purpose. Yes.
What also materials to explore this kind of materials? Only X-rays or other techniques?
From a structural point of view, X-rays give a striking information. So without artifact or something like this, so I think it's a good characterization treatment, a good characterization analysis. Then there are other characterization analyses that we can perform on the biomaterial from other points of view, for example, mechanical tests, biological tests, or the release test, as I said before. But X-rays, I think, are fundamental for the characterization of structure without artifacts, and I found them useful, very useful.
Yes, it is possible for our students to visit your lab and for analysis or.
The lab in which I work, my group leader is Cinzia Giannini, as I said, and if you are interested to talk about measurements or to talk about collaboration, you have to talk with her, because she is the the group leader. And I wrote her email in the end of my PowerPoint. If someone is interested in, I can give the email.
Thank you. Nice to meet you again. Thanks for this very, very nice conference. Thank you. Thank you, Professor Konkagul.
Thank you, Dr. Hammoite, Professor Hammoite. Thank you so much, Alberta Terzi, for this presentation. Very interesting presentation. I think. Thank you, all of attendees in this session. I think there is no question, Professor Hammoite. Are we okay?
Okay.
Okay. We can finish this session, I think.
Okay, thank you.
Thank you, Alberta. Have a great day.
Bye.
Next time it's sunny day.
Yeah.
Bye.
A pleasure to see you this evening with another conference of Professor Mamia El Ghazi from the University of Hassan II from Muhammadiyah, moderated by Professor Salhi Samira, and the third one of Professor SMAIL TRIKI, moderated by Professor FOUAD MALEK. See you again. Thank you so much.
Thank you.
Thank you so
Bye.
much. Bye.
Bye. تبارك الله، كنا ننتظرك يا أخ جودة، كيف حالك؟